Different rigging models have different trade-offs. Traditional methods are computationally cheap. Finite element models are more accurate but more expensive. Shape matching methods try to balance this trade-off. The goal of our method, however, is to avoid the trade-off altogether by making physically based elasticity much cheaper. We motivate our method with a simple flour sack geometry. We control the simulation with 4 spheres at the corners instead of a skeleton. Our method deforms an underlying hexahedral lattice. If we select one of the controls and move it, it causes a deformation in this lattice. Now we will create a simple animation. Notice as we move the controls, the volume-preserving nature of our deformer creates interesting shapes. Our method is also able to handle self and body collisions. Here we compare our stability to that of warp stiffness. With an insufficient number of CG iterations, warp stiffness becomes unstable. But even if we increase the CG iterations to 200, warp stiffness also is unstable. Here it is from a different view. Consider this production character. Here is the original production rig, which, though it got a very good fleshy look, could not eliminate self-collisions. If we apply our technique, we get a deformed lattice that is driven by the skeleton and does not have interpenetration, and also exhibits nice volumetric bulging. The resolution of collisions eliminates pinch regions, which makes later cloth simulations easier. Here is a blend between the production rig and our result. Our method also extends to dynamics. Notice the inertial effects on the character's belly. Now we compare the quasi-static result to the dynamic result. Now we compare our production rig to our result. Notice how our result has a much better appearance due to volumetric bulging and collision effects. Pay attention to the highlighted regions, such as the shoulder and its self-collision, the elbow and its exhibiting of collision bodies. Now we consider a hand example. The hand is especially difficult because of the many degrees of freedom. This makes augmenting a linear blend skin with pose-based deformation hand-modeled shapes much more difficult. As we close the hand and the finger, observe how the lines of contact due to self-collisions are much cleaner on our result. Observe the highlighted regions as we play again. As the finger closes. As the hand closes to make a fist. Here it is from another angle. As we look from the top, the knuckle exhibits much more definition. Here, our fingers look less uniformly cylindrical.